Hey everyone, I'm JieZhou from the University of Rochester. Today I'm going to present my ongoing work and a future project for my thesis, retrofit memory safety to low-level software incrementally. Memory safety is a very old problem and conceptually it's pretty simple, such as out-of-bounds access or use after free. But it's extremely to make memory safety errors if you program in C or C++, and it's extremely challenging to efficiently prevent or catch memory safety bugs. A recent report from Microsoft shows that in the past 15 years, almost every year, 70% of all the computer security vulnerabilities are memory safety related. I will first talk about the motivation for the research direction choice, and I will talk about my current project about extending a safe dialect of C called checked C with temporal memory safety. And I will very briefly talk about a future project called checked code integrity. So there are three major research directions for memory safety. First is static analysis. They can analyze a program to catch memory safety bugs without running them, but they often suffer low coverage and hard to scale to large programs. The second direction, and might be the most researched direction, is transformation by compiler and or binary writer. So those tools automatically transform the program to insert checks to catch memory safety bugs dynamically, but they usually have a very high performance and memory overhead. The third direction is a new safe programming language, so they can provide safety by construction. But the downsides are they require many rewriting efforts, and they often have a backward compatibility issue with the existing code. Although with such disadvantages, I am particularly interested in this direction because it provides strong security guarantees by construction, and a well designed and implemented safe language can minimize the many writing efforts and the compatibility issue. So first, extending check C with the temporary memory safety. Temporary memory safety is mainly about preventing use after free bugs. Use of after free bug is simply that after a memory object is deallocated, any dereference to the dangling pointer is undefined behavior, and it gets particularly dangerous when the old memory object is filled with some new invalid data, and then the dereference to the dangling pointer could leak data or corrupt data. There are mainly three types of use of the free solutions. The first is a safe memory allocation, such as never reusing virtual memory and using garbage collection or reference counting techniques. The second is dangling pointer invalidation. So the runtime system keeps track of which pointer points to which memory object, and at memory deallocation, invalidating all the dangling pointers. The third type is dynamic identifier or key lock checking. So each memory object is associated with an ID, and at a pointer dereference, the ID is checked for validity. At memory deallocation, the ID is invalidated. The one key observation on previous works of dangling pointer invalidation and dynamic key check is that the common reason why they are slow is that they use disjoint data structures such as hash tables or trees to maintain point object metadata. And querying and updating metadata is slow because they first have to find those metadata. So this made us wonder that using a in-place metadata scheme such as fat pointers should be very fast. So our proposed solution is to adopt a in-place dynamic key-lock check mechanism for temporal memory safety. This high-level idea was actually first proposed by a dialect of Pascal called UW Pascal about 40 years ago, but no one has evaluated this idea for modern C. So we are extending check-C with the temporal memory safety. Check-C is a new extension to C that focuses on memory safety and type safety. The reason for choosing check-C is that it lays a very good foundation for adding temporal memory safety to C, because it provides easy incremental conversion efforts from C, and it has very good backward compatibility, and it has low performance overhead for spatial memory safety. So we are adding new checked pointers to check C. The first is a new checked pointer to singleton objects. Besides the raw pointer, this checked pointer has a offset key field. For example, this struct cat object has a lock allocated right above it, and the checked pointer has the key that matches the lock. The temporal memory safety check is simply that to see if the key matches the lock. Although we disallow pointer arithmetic on this type of pointers, sometimes a program uses the address of operator to create pointers to the middle of a object. So we add a offset subfield to the metadata field to help compute the location of the lock. And for array objects, because arrays can be arbitrarily large, the offset scheme might not be large enough for arrays. So we add a third field uh, that directly stores the location of the lock. And here are some preliminary evaluation results. We refactored several ODM benchmarks, and we measured the performance overhead caused by the metadata of the pointer itself without and with the dynamic checks. So the metadata itself incurs 16% performance overhead on average, and the metadata plus the dynamic check slowed down program by 20%. These two data don't look very good now, but first, the older benchmarks are a pointer-intensive benchmark suite, and all the previous works that use metadata for pointers show higher performance overhead and memory overhead for their pointer-intensive benchmarks. In the second, we can apply more aggressive data flow analysis to remove redundant checks. There are three major future works. First is to add multi-threading support because our checked pointer has more than one field. Second is to refactor more and better test programs because older benchmarks are too small. And the third is to apply more aggressive data flow analysis to remove redundant key checks. Next project is called checked code integrity. The problem is that in a program mixed with a safe and unsafe language, the security guarantees from the safe part could be broken by the unsafe part. So for example, here is a check C program. Find key is an original C function, and the full function is a checked function, and it has a checked array. But once the checked array is cast to a raw pointer and passed to the unchecked function, no security guarantee is provided. So our research goal is to protect the data used by checked code from being illegally accessed by unchecked code. To that end, we first need data classification. There are three types of data. Checked only data are only accessed by checked code, and unchecked only data are only accessed by unchecked code. And the third type of data are accessed by both type of code. For example, the array in this full function is checked unchecked data. And we plan to protect all the data that are touched by checked code. So about risk directions, we first need the pointer analysis to classify the three types of data. And to protect the checked only data, we'll seek help from our address space isolation techniques. And for protecting checked unchecked data, we'll try to find the solutions by retrofitting pointer and object metadata to unchecked code. To summarize, my current project is extending a safe dialect of C called checked C with the temporal memory safety. And my future project is to protect the safe part from the unsafe part in a program mixed with both safe and unsafe languages. Thanks for listening. That's all what I have today.